So this is a very handy result when working with sequences. Very often using algebra, we can reduce the sequence down to just looking at things like some number r raised to the power n. And this immediately gives us a way to compute these kinds of limits. So if you have a sequence of r raised to the power n, it will converge so long as r is strictly greater than -1 and less than or equal to +1, right? So it will converge in this region. And for any other value of r, if r is too big, if r is greater than 1, or if r is less than or equal to -1, then the sequence diverges. And what's going on here to actually calculate that limit, if r is strictly between -1 and 1, the limit of this sequence will be 0. If r equals 1, the limit of the sequence will just be 1. So if you can break down a sequence you're looking at into just sequences of some number raised to the power n, this gives us a way to compute them. Now, before I end today, I also want to talk about some more tools for figuring out whether or not a sequence converges. So I'll want to know if sequences are increasing or decreasing at some particular term. So let's say you know that a of 10, a sub 10, the 10th element in your list, is less than a11, the 11th term of the sequence. Well, the sequence is increasing there. If this is true for every element of the sequence, if you know that a sub 1 is the biggest element of the sequence, and then a2 is less than a1, and then a3 is less than a2, and so on, and this is something that's true for all values of n, I guess I would call that a decreasing sequence, just like we have decreasing functions. Similar for increasing sequences, every next number on the list has to be greater than the number that came before. Now, increasing and decreasing are sort of opposite ideas, but they are similar enough that it's convenient to have a word that means either increasing or decreasing. And again, this is a very technical term. So we call a sequence monotonic if it's either increasing everywhere or it is decreasing everywhere. So some of these sequences are increasing, right? Because every next item, every next number in the list of numbers is bigger than what came before. Some sequences are decreasing because every next number in the list is smaller than what came before. But some sequences are not increasing and also not decreasing, right? If I have, well, this function right here, sometimes it's increasing, sometimes it's decreasing, but it is not always increasing. It is not always decreasing. So monotonic is the special name we give for functions that always increase or always decrease. And this is a handy thing to recognize because we can also try to figure out if the sequence is bounded. So if all the numbers on the list are less than some number m, the sequence is called bounded above. If all the numbers on the list are greater than some lowercase m, I'll call that bounded below. So you can say that all the numbers on your list are less than something. All the numbers on your list are greater than something else. If both of those are true, we'd call the sequence bounded, right? So you could have a sequence that's only bounded above. You could have a sequence that's only bounded below. And if both of those are true, we just call the sequence bounded or bounded on both sides. And so the sequence I started out this talk with, where my formula is just n divided by n plus 1, this is a bounded sequence because my numbers on the list are always bigger than 0, just looking at this fraction, and they're always less than 1. So what good is that? The benefit to this is that bounded monotonic functions or bounded monotonic sequences must converge. That's it. That is the big idea thing that we're looking for here. So the idea in the picture is pretty simple. I know that either all of my values of the sequence are, increasing, or they are all decreasing. Again, because it's monotonic. They have to increase forever or decrease forever. But I also know that there's some threshold, right? Some upper bound that is stopping the sequence from diverging. Well, then the sequence actually has to converge. Now, it might not converge to exactly the upper bound we have found, but we at least know that it does converge somewhere. So this is one test that we can use to say whether or not some sequence converges. All right, I think that is enough for today. I will catch you next time.